All right, this will be the last little bit that we'll talk about with respect to water and ion transport through polymers. And I wanted to come back. We've had a fairly detailed look at the water transport through polymers in the sense of hydraulic permeation and its relation both to desalination, things like reverse osmosis, but also up and coming applications like organic solvent nanofiltration, which are pressure-driven flows as well. I'd like to come back now to an expression that we derived starting from Fick's law for the flux of salt across a membrane, or a solute across a membrane, under the impact of a concentration gradient, and take just a bit more detailed look at what happens when the solutes that are undergoing transport are not neutral, when they're electrically charged. And we'll look at a simple case today, and I'll ask you to think about how that would be extended to more complex cases here in a moment. And so the bottom line is to understand how this result arises in situations where the solutes that are transporting through the membrane under concentration gradient are electrically charged and are dissociated ions. And so you can think about this in the simplest case as something like sodium chloride transport from an aqueous solution on one side of a membrane into an aqueous solution on the other side, and a gradient in that salt transport drives salt flux. First thing, one of the most important factors distinguishing ions from simple solutes like gases and simple liquids as they transmit through membranes is that ions rarely travel alone. In their crystalline form, ions are typically dehydrated. At least simple salts like sodium chloride would be dehydrated in a crystal lattice. If you take that crystalline material and dissolve it in water, these ions are then surrounded by water molecules, and the electrostatic forces that come about by having a fixed charge on these ions really attracts water. So you can see here on the negatively charged chloride, the protons on the water molecule are aligning so that they get maximum exposure to that negative charge density. And likewise, in the positively charged sodium, you see the water molecule turned around so that the negatively charged end of the oxygen has great exposure to the ion. And as these ions diffuse through water, and in fact through most polymer membranes, the water surrounding these ions goes with them. That's so-called water of hydration. And to give you an idea of what that means, this is a table from the old literature of effective ionic diameters of ions in picometers, and the top number in each of these, under each of these ions, is the unhydrated, that is so-called crystal diameter, and the number under it would be the effective diameter in solution, hydrated diameter. And the difference between these two numbers reflects the waters of hydration that the ions carry with them as they diffuse through solution, and also as they would often diffuse through other media. One of the things that you can notice is that there is a trend in the relationship between hydrated ion size and unhydrated ion size. So if you look down this column of monovalent ions, lithium has the smallest unhydrated size. And all of these ions have a +1 electrical charge on them. And so that means that the lithium has a significantly higher charge density, that is unit charge per unit volume of the ion, than something like cesium. And the high charge density of lithium gives it a high value of hydrated ionic size. So the high charge density of a small ion like lithium attracts a lot of water around it. And the hydrated size, for example, of cesium is not too far different from its dehydrated size, indicating that once that +1 charge is spread out over a much larger region in space, the ability of cesium to attract water of hydration is much reduced. And so what you find is something that is at least initially perhaps counterintuitive, that the ions migrate through most materials, most polymers, and in solution based on their hydrated size. And so down this column, for example, of monovalent ions, starting with lithium, it has the highest hydrated diameter. Cesium has the lowest, along with rubidium. And so the order of transport of these ions in solution is lithium is slowest, cesium and rubidium are fastest, despite the fact that if you just looked at the absolute size of the ion, lithium would be the smallest ion. The smallest ion has the highest charge density, attracts the most water, and that water moves with it as it undergoes diffusion. There are a couple of really important exceptions to this. One of them are the ion channels that are in your body that regulate ion transport across the cell wall. And there are very specific interactions between ions and the proteins that line those ion channels that actually allow the ions to go through in their dehydrated state. And so an ion like potassium can go through these ion channels thousands of times greater than sodium. Even though potassium has a higher dehydrated size, it fits perfectly into the channel to take advantage of the interactions between the channel wall proteins and the ions to strip away its water. Sodium is too small to undertake those interactions and is blocked largely from transmitting through such ion channels. With this exception, though, in most cases, the ions are transporting with their waters of hydration, and the smaller the ion is, the higher its charge density and the more water it attracts with it. This also means that when ions diffuse, for example, through a polymer, that it's not just ions that are coming across the polymer, they're also bringing water with them as well, and that has some implications for the net flux of water and ions across membranes. We'll start by coming back to things that are very basic to describe a transport of any species through a medium, and we're going to consider the charged ion diffusion through a neutral polymer or aqueous electrolyte solution. It turns out that I'll ask you to consider later the changes to this derivation that would come about if the polymer were not uncharged. But in general, we can write the flux of a component under a gradient in chemical potential, and this can be a neutral component or a charged component, in terms of the mobility of that species through the medium and its concentration. So this is just a basic flux law relating flux to chemical potential. You would recognize this in more of a fixed law type formulation when we use the Nernst-Einstein equation to make the connection between the mobility of the species and its diffusion coefficient, and put that into this relationship, which we'll do here in a moment. The chemical potential is written in the usual way, except if a component is charged or can respond to an electrostatic field, to an electric potential, we have an additional term that tells how many joules of energy are contributed to the chemical potential as a result of a field acting on a charge of Z sub I. And typically, this form of the chemical potential, when it includes these electric field effects, is called the electrochemical potential. But the only distinction from what you would normally call a chemical potential is the inclusion of a term that includes the effect of the electrostatic field on the chemical potential. And what this recognizes then is that an electric field can drive the transport of charged species through a medium. If the species is uncharged, an electric field difference doesn't produce any flux. And it's only when species are charged that they respond to these electric fields. Z sub I here is a charge on the ion. And so for sodium chloride, Z would be +1 for sodium and -1 for chloride, and that again indicates what you can see is that an electric field would act in opposite, would drive ions in opposite directions depending on their charge. So that's taken care of here. Just as an aside, the Faraday constant appears in here, and you learned this, I'm quite certain, a very long time ago, and this is just a reminder that this is it's the number of charges in a mole of charge. It has the value that's shown here, but it appears all throughout the electrochemistry literature, and I find this useful just to have a little reminder from time to time. Also, remember our friend Volt is the guy after which the electric potential is named, and it is the potential energy per unit charge that's associated with an electric field. It's also described the electric potential at a given point in space is very directly related to the amount of work that would be required to bring an ion from infinitely far away to a given point in the solution that has a given electric field. So the electric potential is related to the reversible work required to bring an ion in from infinity to a given point in a medium. Okay, so we need the gradient in electrochemical potential for the flux expression, and so we can differentiate the electrochemical potential to get the expression that's shown here, and now combine that with the Nernst-Einstein equation and write the flux of an ion in terms of its diffusion coefficient, its concentration, gradient and log of its thermodynamic activity, and then a term that represents the effect of the field on the flux. And this is the basic starting point for analyzing the transport of charged species through aqueous media or through membranes, etc. In a solution, the ion activity is typically taken to be proportional to the ion concentration, and this assumes that the activity would typically be written as an activity coefficient times concentration. What we're interested in here are gradients in the log of the activity, and so this assumption basically assumes that the gradient in the log of the activity coefficient doesn't change much from one point to another in a solution. If that's not the case, you can keep this expression in terms of an activity coefficient and a concentration. It would typically not be possible to easily get analytical solutions at that point. But this is often a good approximation, and so then we write the gradient in the log of the activity as shown here to get the boxed equation. And now you start to see an expression that looks for all the world like Fick's first law, right? Diffusion coefficient times the gradient and concentration. And then an extra term that gives the effect of the electric field on the flux. And it recognizes that the ion diffusion coefficient that's important for having ions migrate through an electric field and for ions migrating in a concentration gradient is exactly the same diffusion coefficient. There's one diffusion coefficient for an ion that is migrating through a concentration gradient, through an electric field gradient, or through some combination of the two. And so this is called the Nernst-Planck equation, and it'll be the starting point for analyzing the flow of salt through solutions and through membranes. We can also formally include the effect of convection. Strictly speaking, this is the flux of an ion relative to the mass average velocity in the system. and we can account for the effect of convection in the usual way by including a convective term in the expression for the total flux. So the total flux includes a piece that is driven by gradients in concentration and electric field, and also a piece that could be driven by just the bulk flow in the system. And what you might imagine here is an aqueous electrolyte flowing through a pipe that's also under an electric field gradient. There'll be transport of ions just due to the pressure-driven flow of fluid through the pipe, and the effect of the electric field will also be causing a diffusive flux of ions that is above and beyond whatever the convective field would be. And so this is the final expression for the total flux of ions through a liquid media or through an uncharged or through a membrane. We can put this flux expression into a general expression of conservation of mass. This is straight out of Bird, Stewart, and Lightfoot, that the time rate of change of the concentration of any species at a point in a system under study depends upon the divergence of the flux and the net rate of production of that component by chemical reaction. Okay, this is basic mass transport phenomena. Typically, we're going to be most interested in systems where that don't involve chemical reactions, so we will remove that term and restrict the analysis to non-reactive systems. We can write the mass balance or combine the mass balance expression with our expression for flux to get a revised version of the mass balance equation shown in the middle of this equation. If the diffusion coefficients are constant, we can go ahead and work some of the calculus out as shown here, and I'll do just a little more algebra on that to basically beat it into the final form that we need for analysis. And so if any of these terms aren't or steps aren't clear, please ask me, or better yet, ask Rahul. And we assume the system is incompressible, so the divergence of velocity is 0. And we've come up with the final expression for the transient expression for the conservation of mass that's shown here. So we'll start with that in terms of modeling ion transport through solutions and through polymers. And so now we consider a case, for example, where we have sodium chloride or we have salt in solution, potentially diffusing under the effect of either concentration gradient, electric field gradient, or potentially a convection. We're going to solve this problem in a moment in the absence of convection, but I leave it in now for completeness. We can write one mass balance on the cations and one on the anions. There are two separate chemical species, and each will have its own electrochemical potential and will be driven to transport by its concentration gradient and the way the electric field acts on it. And so I'll use D+ for cations and D- for anions, likewise for concentration and also for charge. Now, these two equations initially would appear to be independent of one another. They involve concentrations of different species, they involve diffusion coefficients of different species, but in fact they are coupled. And they're coupled by the principle of electroneutrality. And what this says is that we cannot have an ion isolated by itself in solution. It always has a neighboring ion of opposite charge that keeps the overall solution, or in a polymer, the overall membrane electrically neutral. And this assumption is a bedrock assumption in electrochemistry of solutions and transport through polymers. There's a nice description of how little solutions can deviate from electroneutrality on a couple pages here in John Newman's book. But for all intents and purposes, over any sort of measurable space in a material, electroneutrality is maintained. And what this means is that the concentration of cations and the concentration of anions are linked through this expression. And that means that their mass transport is linked. And so these two equations, which describe the mass balance for cations, mass balance for anions, are linked through the requirement of electroneutrality. Now, we can introduce the number of cations and anions produced by dissolving or dissociating a mole of an electrolyte and a binary electrolyte, a monovalent electrolyte like sodium chloride. We can define the concentration of that electrolyte as follows, as C plus divided by the number of cations produced by dissociating a molecule of electrolyte, and that's equal to C minus over the number of anions that are produced. And so we talk about salt concentration in terms of for example, in a 1 molar solution of sodium chloride, it will have 1 mole per liter of sodium, 1 mole per liter of chloride, and we can talk about the salt concentration being 1 mole per liter. And those are three ways of saying exactly the same thing, because the system has to be electrically neutral. And that allows us to write the cation and anion concentrations in terms of the just what I'll call the salt concentration in the medium. And show an example here for how that plays out for a monovalent salt like sodium chloride, where nu plus and nu 1 are both 1, and also for calcium chloride, where the concentration of chloride is always going to be half the concentration of the concentration of chloride is always going to be twice the concentration of calcium. So in a 1 mole per liter solution of calcium chloride, the salt concentration that we would refer to as 1 mole per liter, concentration of calcium is 1 mole per liter, and the concentration of chloride is 2 moles per liter. And this concept of electroneutrality helps us connect these concentrations. Now, with this in mind, I can rewrite the mass balances for cations and anions in terms of the salt concentration. Now, that is shown here, and we have simply inserted for C plus, C times nu plus, and for C minus, C times nu minus. Now, working with these revised equations that again express the transport of cations and anions in the solution or in the membrane, we can subtract the anion balance from the cation mass balance. Nothing prevents us from doing that. And we get the equation that's shown here, and I'll rewrite it on the next slide. And essentially what this does is it connects the concentration gradient in a solution or in a polymer with the electric field gradient. And what this means is that anytime you have a concentration gradient in an electrolyte solution or a concentration gradient in electrolyte transporting through a membrane, it induces an electric field or an electric potential. It is that electric potential that keeps the ions in close proximity, that enforces electroneutrality. By the same notion, if you apply an electric field gradient, then this also inherently induces a concentration gradient, and the two are tied together as shown here. We can take this result now back to the overall mass balance, for example, for the cation. Could also do this for the anion. And we now have an expression here for the electric field that writes it in terms of the concentration. And so we will replace this term with this one. And the result at the bottom of the page then has the, for the cation mass balance, has the concentration of salt at every position where there is a derivative. And so now, even though there is an electric field in this system that keeps the ions together through electroneutrality, we can express the mass balance without actually explicitly calculating that electric field. because it's connected as shown here. And we can further carry out a bit of algebra to put this in a more familiar form. Let me get one more slide to get it to the final form. So this is again just algebra. And what you start to see is that this version of the mass balance starts to look an awful lot like what? Fick's second law that we talked about at the beginning of the semester, right? For a constant diffusion coefficient, and if this is the diffusion coefficient, this looks exactly like Fick's second law, and that means that all of the solutions that are in Crank and the analogous solutions that are in Karshalaw and Jaeger for analogous problems can be applied to electrolyte solutions and electrolyte transport through polymers. So this brings us to a really powerful point in terms of being able to analyze the effect of transport of charged species through polymers or through aqueous media. And so it's typical to write that this term as the salt diffusion coefficient. And if you simplify that down just a little bit, the effective salt diffusion coefficient depends on both the cation and anion diffusion coefficients in the system. Now, this assumes that there is not a big discrepancy between the concentrations of cations and anions in ion exchange membranes, some of which we talked about earlier. That will not necessarily be the case, and this diffusion coefficient gets modified slightly to also have the local concentrations of cations and anions in the membrane. But this is the case for a transport through aqueous solution or transport through neutral polymers. It looks exactly like the convection diffusion equation that we would have for neutral components, with the understanding that the diffusion coefficient now depends on the diffusion coefficients of both species due to the requirement of electroneutrality. And so if the diffusion coefficients of cations and anions are the same, you get a very simple result that's shown, trivial result that's shown here. Now we come back to the salt flux for a desalination membrane and the equation that we wrote based on integrating Fick's law. We start with a more general equation that we've just derived, where D is that salt diffusion coefficient. And in a case where the membrane is operating at steady state and where convection is not important, which is often the case in the operation of desalination membranes, we can solve Fick's second law in a very simple form. And now I've added an S as a subscript to this D to explicitly recognize that this is neither the cation or anion diffusion coefficient in the membrane, but it's what we call the salt diffusion coefficient. It's this guy. And so from this expression, we can integrate it to give the concentration gradient across the membrane, and we can put that into Fick's law with constant diffusion coefficient, and get the relationship between the salt flux and the concentration difference inside the membrane. It is typical then to connect these internal concentrations to the external concentrations using a partition coefficient. And there may be a variety of thermodynamic models that can be used to relate the concentration of salt inside the membrane to that outside the membrane. Typically, over narrow ranges of salt concentration inside the membrane, we would assume that the partition coefficient for salt at the upstream face and at the downstream face of the membrane were the same. And with that assumption, we can replace the concentrations inside the membrane with those in the external solutions, which are the ones that you can measure physically in an experiment. And now you start to see that this equation looks an awful lot like this one, especially when you make the connection that the what we're calling salt permeability here is just the diffusion coefficient of salt times its partition coefficient. And so that gives us a connection between the performance equation that we often use when describing ion transport in concentration-driven transport through a membrane, and its relationship to the transport of the individual ions. Are there questions about this? We're going to stop and change topics now. Okay. Now we need to have a, I don't know if anyone's ever had a serious discussion with you about pervaporation, but we're gonna do that today. So, what is pervaporation? Has anyone heard of this? Gosha, you must have heard of this. And
Yeah, I've heard of it. It's old type of sport.
Yep.
Can you pull a vacuum on one side of the membrane? And it causes the permeate to become a vapor.
Yeah, so we have considered so far, if you think about kind of in kind of a diagram of transport properties, we've considered cases where the membrane has gas on both sides. We've considered a case where it has liquids on both sides. What's left? There's liquid on one side and gas on the other. It's just, or vice versa, which would also be pervaporation. And so there's a number of places where this is being applied and where people are looking at applying it. For example, there's a whole field in membrane science on solar desalination. And basically a feed solution is of salt water is heated across a membrane, and you form a vapor phase on the downstream side that essentially is pure water. It's been used quite a bit for separating azeotropes, so water alcohol mixture. We can talk a little bit more about that, but essentially what is done is a liquid feed of a mixture that you want to separate is fed across the membrane, typically at low pressure, just enough pressure to drive the fluid through the membrane device, and then on the permeator downstream side of the membrane, conditions are created such that the permeate is a vapor, and so this implies that the components that are in the feed that are transmitting across the membrane will vaporize, and that a situation has been created where they do in fact vaporize. And the way that is typically done is by creating a vacuum on the permeate side of the membrane. Now in the laboratory, we would do that typically with a vacuum pump. In industrial practice, that's not the way it's done, because that is that's a hideously expensive way to create a vacuum. What's done in practice is something that is elegantly simple. And so you typically have a liquid feed, and it's often at high temperature, near but not at the boiling point of the mixture. And it contacts the membrane. The pressure is low downstream, and as a result of that, any liquid that permeates across the membrane emerges as a vapor downstream. Now you've got a gaseous permeate. If you take that to a condenser, what happens? It condenses, and when you condense a vapor, what happens to its volume? Is it reduced a little bit? A lot, right? Maybe 1,000-fold, right? Hundreds, factors of hundreds. And if you constrain that mixture in a fixed volume device and reduce the volume of the mixture by a factor of 100, what has to happen, and the temperature is roughly the same, what has to happen to the pressure? It goes down. And then what you wind up pumping is a liquid and not a vapor. And I've seen, basically tens of thousands of gallons per hour ethanol water pervaporation units operating with a downstream pump that would be no bigger than some of the ones that are in the laboratory. It requires very little energy to pump a liquid, a lot of energy to pump a gas. And if you organize it such that this condenser is operating at like cooling water temperatures, then you can perform this step at relatively low energy. And that's one of the advantages of pervaporation over things like distillation. And this is showing some of the history of pervaporation starting in the 50s, going up through first commercial applications in the mid 90s. These are applications where pervaporation has been applied. It's used in things like dehydration of alcohols from water and azeotrope breaking and dehydration of other organics. People have looked at it for salt removal. This is not as economic as using things like reverse osmosis. It's actually, I don't know if this may be of no interest to any of you, but there are products on the market that call themselves beer but have low to no alcohol in them. Exactly. How do you think that happens? That's not. You think it's like a special wheat or something, right? That doesn't produce alcohol? No, maybe not. It's pervaporation. It's used to remove alcohol. Now don't let that turn you off from this unit operation. But that is a commercial application of this technology. And then there's a number of other applications that have been studied and are under development. The two materials that are most widely used in this application today are very simple polymers. It's silicone rubber we've seen before. It's one of those polymers, Christine, it's almost like polyethylene oxide. It's good for everything. So you see silicone rubber in gas separation applications. It shows up in a lot of controlled delivery applications, and here it is backing in pervaporation. It is very hydrophobic, and so it will remove low concentrations of organic from water efficiently. On the other hand, cross-linked polyvinyl alcohol, or PVA, is a hydrophilic membrane material. It is used to remove water from organics. Now, there are other polymers that have been tried and in some cases used. There have been polyimides that have been tried in this application. For example, water is so much smaller than ethanol that even in traditional polymers like glassy polymers used in gas separation that might favor the solubility of the organic, the diffusion selectivity in favor of water is so great that things like polysulfone and polyimides and so forth are water selected in water alcohol separations, and they've been tried in some of those cases. But these are the ones that are that have the longest track record in the field. This is a table from Richard Baker's book that describes some of the membranes that have been used, just for your reference. But here's the bottom line on why pervaporation is of interest as a separation. So you recognize this if you're a chemical engineer as a liquid phase concentration and vapor phase concentration. This is the case of acetone water separation, and this is the vapor liquid equilibrium you get if you just boiled acetone at a certain concentration. This is the concentration of the gas phase above it. If you do a pervaporation step with acetone, say at this concentration, and using a silicone rubber membrane that is selective to acetone but not water, you can increase the permeate acetone concentration remarkably. So pervaporation is coined from two words, permeation plus evaporation. Pervaporation. And the idea is that you get the benefit of the evaporation step because you are converting liquid feed to gaseous product, plus any additional benefit that would come from any selectivity that the membrane would have for those two components, pervaporation, permeation plus evaporation. On the other hand, if what you wanted to do was extract the water from this mixture, so this would represent taking the acetone off in the permeate as the desired product. If you wanted to extract the water in the permeate, you could use a hydrophilic membrane, and look how it changes the VLE plot here. Now you can go to very high concentration of acetone concentration, and the permeate has almost negligible acetone, so you get almost pure water out. So depending on the membrane material and the components being separated, you can select for, in this case, the more hydrophobic acetone or the much more hydrophilic water. It's also worth noting that this is again, it's a combination of permeation plus evaporation. And in the case of the silicone rubber, which is acetone selective, the vapor-liquid equilibrium is acetone selective. Acetone is more volatile than water. In this case, the membrane and the normal thermodynamics work together, so you get a synergistic increase in separation ability because both the vapor-liquid equilibrium as well as the membrane are selective for acetone. In the case of the hydrophilic membrane, you're actually, nothing has changed in the vapor-liquid equilibrium, so the evaporation part of this step would still look like this, but the membrane is so much favors the transport of water that you overcome that and permeate mainly water. In this case, the vapor-liquid equilibrium and the membrane separation are working against one another, and you can have both cases in this application. This is showing the case of ethanol water separation, and this has been one that's been looked at a lot for pervaporation. Do you have any idea why?
Is it true?
Yeah, and why would you want to get out beyond the azeotrope?
To make fuel, I think.
Okay.
Like sell it as a solvent.
Sorry?
So the ethanol solvents.
Yep, you can use it as a solvent. What else is it? Sorry?
Fuel.
Yeah, so this is, the way that fuel grade alcohol, ethanol is made is by a fermentation process. For example, companies like Archer Daniel Midland, Tate & Lyle, and others who are big into the fuel grade ethanol production will take corn into the intake of a plant, and they derive an enormous number of products from the fermentation of corn and byproducts like animal feed, products that we know and love like high fructose corn sugar. I'm sorry, high fructose corn syrup. They were prohibited from calling it corn sugar, although not without a significant try at doing that. And in these plants, the high fructose corn syrup for sodas and candies and Lord only knows what else is shipped out in rail car loads. Some of these plants are also set up then to make alcohol for fuel. And the way that works is that from the fermentation process, you get what they call beer, and it is on the order of, it's fermented up until about 10 to 15% ethanol. It enters a distillation column that can easily take it up to about 50%. You get a lot of driving force down here, and then would often go to a second distillation column that would take it further, and that second distillation column would be pushed in terms of temperature and pressure to get as close to the azeotrope as possible. And so if you go to one of these plants, you see this large amount of low content alcohol coming into two distillation columns, and that reduces the volume of the required feed enormously by about half, but increases the alcohol concentration quite a bit. And so those two initial distillation columns then feed a single second stage distillation column that brings the concentration of alcohol up into the region of the azeotrope. The conventional technology, and what's most widely practiced today, is to then take that alcohol, which can be as high as like 90 weight percent ethanol, and put it through molecular sieves to dehydrate the alcohol, typically to something like 99% ethanol or something in that range. And molecular sieves are an adsorbent-based technology. They work very effectively for this application, have a long track record, but it's very energy intensive. And there have been people who have tried to use membranes in these applications to reduce the energy intensity. This is showing what would happen with a hydrophilic membrane. A lot of the membranes that are used in this application are hydrophobic, trying to pull the water out through side sieving mechanisms. Now, just as a last little, one last thing, when these plants are running, they're making, one side high fructose corn syrup in rail car loads, and on the other side of the plant, they're making 99+% ethanol in rail car loads that then go to refineries and are blended in with gasoline. And so what I want to discourage you from looking for ethanol tankers on the rail and trying to get your next drink there. What do they do to it? Sorry?
Like, did I trigger it? I don't know.
Yeah,
What's the
there's
word in
no
English?
Yep. So finally we get on to alcohol and sparks of discussion. How do they do that?
How do they have the benzene?
Mhm.
Oh, I don't know.
All right, this is a great chemical engineering problem. You are making fuel grade alcohol, almost not quite medical grade, but almost medical grade alcohol. It's going to go and get blended with gasoline to make the gasoline that goes into your car. How would you denature the alcohol? Put about 5% gasoline in it. And so at the point where it goes into the rail car, it's blended with a small amount of gasoline that denatures it. Last little tidbit. The alcohol that goes into the rail cars is, typically better than 99% ethanol. It's way past the azeotrope. What's required by fuel grade standards, by ASTM, is on the order of 95, 96%. Why would you purify it to above the requirements for fuel grade alcohol?
Start taking water from the air.
Ethanol, as you may know, is hydrophilic. In fact, it's almost hygroscopic. And so as the ethanol is transported from the point where it's made to the refineries and then ultimately to the blending process, there are opportunities for it to pick up water. And so you have to purify it above fuel grade standards so that it doesn't drop below the fuel grade level by the time it gets to the folks that are gonna do the blending. Otherwise, they send it back. Anyway, so this shows a variety of different materials: polyvinyl alcohol, cellulose triacetate, and cation exchange membrane that were used in research for trying to do pervaporation ethanol water mixtures. And it just shows that you can dramatically alter the results that you would get simply from vapor liquid equilibrium. You can also use polymers that are very rigid that sort for water, and those are used in this application as well. So this is an example of a flow scheme that brings in low concentration alcohol, 2 stages of distillation, then into the pervaporation. The permeate is recycled back into the distillation column. So it's essentially a closed loop process. There are solids that come out the first distillation column, water out the second one, and fuel grade ethanol or above fuel grade ethanol out the third one. The problem is that, and a frontier area for membrane science in this area, is it turns out that high temperature ethanol water mixtures is not suitable for all polymers, and it's certainly not suitable for a lot of the components like epoxies that are used in modules that are used to put membranes together. And there's been a number of failures at rather large scale in this industry. And so today, most of these units are molecular sieve units. This is an early version of a plate and frame membrane system that's used for ethanol water pervaporation. The membranes sit in here, and so I thought I'd show you just a couple pictures of these systems. The analysis, at least to the first approximation, is that we can view pervaporation as being a permeation plus evaporation step, and we can actually analyze the transport in that fashion by analyzing the liquid vapor equilibrium that gives rise to the evaporation, and that gives a selectivity for evaporation that can be defined based on the partial pressures of each of the components in the gas phase divided by the concentration of the components in the liquid phase. This would be a standard way of, and in ideal solution, these partial pressures in the vapor phase would be proportional to the mole fraction components in the vapor phase. And these concentrations, for example, might be the mole fractions of each component in the liquid phase. And you remember from your studies of distillation in separation processes that these evaporation selectivities would be ratios of the mole fractions of each component in the gas phase divided by the mole fractions in the liquid phase. So this is exactly that. It's the evaporative separation factor. One can also define for the membrane step a selectivity due to the membrane, and write that in terms of the partial pressure of each component in the permeate, the ratio of those partial pressures in the permeate to the same values in the feed. And so we often talk about pervaporation separation factor being a product of a thermodynamic piece that comes from the vapor liquid equilibrium. This is the one you would know from just designing distillation columns, and then a piece that would come from the membrane separation. And these two separation factors can act together, or they can act against one another, depending on the situation. And so one of the areas that pervaporation has been considered for, but I don't believe has ever been applied commercially, but there's been a lot of study, is in cleaning up spills or water that's contaminated with organic, low levels of organic liquids. It's incredibly hard in some cases to clean up, incredibly expensive. And so this is showing for a silicone rubber membrane a correlation of the pervaporation separation factor with the basically vapor liquid equilibrium saturation separation factor. And there are regions where the membrane helps or works in the same direction as the evaporation separation factor, and then there are regions where it is not so helpful. So this is a system that's been used at Applied Biosystems in California to remove low levels of methylene chloride from water. These types of operations could either be done with with adsorption. These systems, absent any other alternative, would be put in a burner and burned, although that's a very expensive way to deal with them. And in a number of cases in the pharmaceutical industry, they're using pervaporation. And you can see one of the issues here is these are small systems. These are not really large scale systems, and that often favors membranes. They often scale down easily or economically. Now I want to tie this back just briefly to some of the discussion we've had with the transport of liquids through membranes and transport of gases through membranes, and we'll start it with with experimental data showing this is just pervaporation of water through a silicone rubber membrane. So there's no separation going on here. This is just to make a point about how the transport mechanism works. And what's being plotted is the permeate flux as a function of the permeate pressure. And so the feed pressure will be atmospheric. It's just water, in some cases hot water, flowing past the silicone rubber membrane, and then on the downstream side, condensing the water vapor product at various permeate pressures. And what you can see, what you could imagine, is that as the permeate pressure rises, the driving force for water transport goes down. And so the flux would come down. What's interesting is to note for each of these temperatures where the flux, the flux is a linear function of permeate pressure, and where the flux goes to zero. So where is that? Think about this. We have liquid water upstream. It's pure liquid water. So what's its thermodynamic activity? 1, okay? Now we have water vapor downstream, and let's say it behaves as an ideal gas. What would be its thermodynamic activity? Ooh, come on now. I was a sophomore once. Material energy balance and steam tables. What's the thermodynamic activity of an ideal water vapor, ideal vapor solution? How's it related to the? Sorry? Yeah. Go ahead.
The ratio of its pressure to vapor pressure.
Say it one more time.
The ratio of its pressure to its saturation pressure.
All right, thank you. Good morning. So the thermodynamic activity of an ideal vapor system is its partial pressure divided by its vapor pressure, saturation vapor pressure. Partial pressure over vapor pressure. Does that make sense? What would the humidity be? Ooh, Santa's not gonna be too happy. We haven't been good on thermodynamics. What would be the relative humidity of water vapor? Yeah, say it again.
Partial pressure divided by saturation pressure.
Times.
Times
Times 100, yes. Okay, got it. All right, so, in the gas phase, downstream in the system, when does the thermodynamic activity of water become equal to 1? When the permeate pressure becomes equal to and if the thermodynamic activity of the water upstream, the liquid water upstream is 1, and the thermodynamic activity of the liquid water downstream is 1, what's going to be the flux? That's right, not. Okay? And so the permeate flux drops as the permeate pressure goes up because you're approaching the thermodynamic activity of the water is approaching 1, it's 1 in feed, 1 in permeate, and there's no flux. Raise the temperature, raise the vapor pressure. So you get a little more, leeway in how high the perm pressure can be before the flux drops off. Raise the temperature again, raise the vapor pressure. Look at that. Basic thermodynamics, right? Okay. And so now remember this. This is our expression for liquid water transport or liquid solvent transport through membranes. I won't belabor all of the variables except to say that the ratio of water concentration in the permeate to that and feed side of the membrane can be obtained from the thermodynamic activity. The concentrations of water at its feed and permeate surfaces are linked by the thermodynamic activity coefficients. If the water is not pure, even if it has not just mixtures of salt and water, but organics in water can also be expressed. The activity of the water can be expressed in terms of osmotic pressure. And we work our way through the details that we've talked about for water and solvent transport of liquids through polymers. And the reason we do this is to get to the bottom line that pervaporation pressure typically run at near ambient feed pressure. And then these terms involving partial molar volume and molar volume are unimportant. And we have these relationships between the activity of the water in the membrane on the permeate side and the activity in the external solution, and likewise in the feed. And as you have already deduced, the activity of the water on the permeate side, which would be the sides under vacuum, for an ideal gas is just the partial pressure of that water divided by the vapor pressure. And so once you let the perm pressure come up to be the vapor pressure, you're out of driving force, and the flux goes to 0. And so the situation that we have in the case of pervaporation is if we have pure liquid feed, its activity is 1. There is an activity gradient or chemical potential gradient through the membrane, and the activity on the downstream side of the membrane is just the partial pressure divided by the vapor pressure. There are very simple relations that we've talked about that give the relationship between the concentration of a component of interest. This is hexane, but it can be water or any other component in a polymer as a function of activity. I've shown a case for hexane sorption in a rubber, and so something as simple as the Flory-Huggins equation can be used to capture that relationship to give the concentration of the penetrant in the upstream side of the membrane. We distinguish two types of transport. One would be hydraulic permeation. This would be the reverse osmosis case or the organic solvent nanofiltration case. You have a liquid on both sides of the membrane, and the feed is pressurized to a pressure well above ambient the permeate is at ambient pressure. Pervaporation, the feed is a liquid and the permeate is a gas, and the feed is at ambient pressure and the permeate is at a partial vacuum. Now, is it possible that the same transport model can describe the transport under both of these cases? Right? If Fick's law is driving the transport of a component through a membrane, the molecules that are dissolved in that membrane neither know nor care that they were in a liquid or vapor state on one side or the other of that membrane. So there should be a common framework and a common model that describes the case where the transport is liquid on both sides, liquid on one side, and vapor on one side, and the third case would be gas on both sides, but we won't talk about that right now. And here is the experimental evidence, or some of the experimental evidence in the literature, that this solution diffusion picture for how penetrants are transported through polymers, where one or two phases contacting the membrane with liquid, it is entirely consistent. And this was work done in these laboratories, or at the University of Texas at least, by Don Paul. And it represents one of the most elegant experiments that is around this topic in the literature. For many years, the thinking and the field of liquid transport through membranes like reverse osmosis grew up entirely separate from the fields of gas separation and pervaporation. There are different communities. You could go to a reverse osmosis membrane conference, or you could go to a pervaporation membrane conference, and they weren't in the same place at the same time, right? And so they're different communities. And what this shows is that the same mechanisms of transport describe the permeation across this entire range of hydraulic permeation out through pervaporation. And so this is hexane transport or flux through a rubber membrane as a function of the activity at the downstream surface of the membrane. And when the downstream surface of the membrane activity is 1, that means that there is no flux, because you have hexane at the upstream side of the same activity. Now, as you back down in the activity of the penetrant at the permeate side of the membrane, in hydraulic permeation, how is that activity decreased on the permeate side? Freddie?
Say one more time.
Remember the hydraulic permeation experiment. That membrane, got liquid on top of it, liquid on the bottom. The permeate is coming out at atmospheric pressure. How did we get liquid to permeate through that membrane? How did we get the activity of the penetrant at the downstream face of the membrane to be less than unit activity, so that there would be a gradient for transport? Look at you, saving you. Oh, and he's pulling out the fire here. Right? Remember, we increase the feed pressure. Lowers the permeate concentration, lowers the permeate activity, and there goes the flux. Okay? And those experiments can be done, depending on the equipment and the situation, up to a certain point. So here the activity of the penetrant is being, at the permeate side, is being reduced by increasing the feed pressure. Now, what's happening in the pervaporation case? What's the situation up here? The permeate activity is 0. What would that correspond to in the pervaporation experiment? Sorry?
Full vacuum.
Full vacuum on the permeate side. Ambient pressure, liquid upstream. Now, as you ease off on that vacuum and raise the perm pressure, the flux starts to drop off. And you raise the perm pressure more and more and more. Flux drops off, and it overlaps with the hydraulic pressure results. In the hydraulic pressure case, we're raising the feed pressure to reduce the downstream activity to drive flow. In the pervaporation case, we always have vapor downstream, and we reduce the flux by allowing the perm pressure to go up. You have a universal curve for flux versus that downstream activity, independent of which mode the membrane is operating in. The liquid's on both sides, liquid on one side and gas on the other. That's beautiful. This ties in very well to the sealing flux value. And if the transport mechanism is the same in pervaporation, hydraulic permeation, and the sealing flux has to be the same. Remember, what was the sealing flux? Where'd that come about? In organic solvent transport through membranes. We said that you could increase that feed pressure, and as you increase the feed pressure, the flux went up. But that didn't happen forever. You couldn't raise the pressure to infinity and the flux would go to infinity. You raise the pressure on the feed side and the flux would level off and become essentially independent of feed pressure. Why was that?
Backside concentration.
Yep, right. Next, redeem yourself.
You can't go below concentrated to zero.
Yep, you dry out the downstream surface is not there. Right. And so then you're done. You can't, no matter what pressure you put upstream, you're not going to increase the driving force for transport. Okay. Here's that experiment from the same paper. Now this is looking at the difference between the concentration of penetrant hexane again, and between the upstream and downstream phases. Again, when you have the upstream and downstream phases being at the same concentration, flux at zero. In hydraulic permeation, we establish a gradient in concentration across the membrane by increasing the feed pressure. As we increase the feed pressure, it drives the concentration at the downstream side of the membrane down, increases the gradient driving force for permeation, increases the flux. And all of these experiments with the solid circles were done with hydraulic permeation, and this line bending over towards the sealing flux was calculated based on data from hydraulic permeation. From pervaporation, you can work backwards along the same line. Now in pervaporation, you have a liquid upstream, and you maintain a high driving force by JC. You maintain a high driving force
Oh, like you bring the pressure close to.
by full vacuum, right? And as you let the vacuum, let the perm pressure come up a bit, this gradient slides, the flux comes down, and you see perfect overlap between the results of pervaporation and hydraulic permeation. All right, I don't want to keep you too long, but thank you for your time today. I look forward to seeing you on Thursday.
People want their homework and then have it. All right.